Atlas is the name of a rocket. It was previously used as a ballistic missile in war, but it is used as in the space program of the United States as a launching rocket. For example, were the first American astronauts with it brought into the orbit, or also probes sent to the moon or other planets with this Atlas rocket launching system. That is according to the Research Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakeshaft on page 50. Hi and welcome. I am trying to learn space science today. Atlas, Auriga and Walter Baade. And after we've done with it, we're going to do body-centered training. And if you participate in the body-centered training, then it's valid hours. Atlas. Launching a rocket used in the US space program. Originally a ballistic missile, it launched the first American astronauts into orbit and sent probes to the moon and planets. So Atlas is the name for a rocket used in the United States space program. The book is from the 1970s already. So used in the United States space program. It was used as a ballistic missile, so for war, but it is here used, for example, to launch the first American astronauts into orbit. So used to launch the first astronauts who performed the United States of America into the orbit, and to send probes to the moon and planets. I mean the other planets. Okay, Atlas is the name of a rocket. It was previously a ballistic missile, but it is used in the space program. It was, for example, used to send the first people from America into space, and it's also used to send probes to the moon or other planets. I'm going to start the camera, and try to say it. Atlas is the name of a rocket. It was previously used as a ballistic missile in war, but it is used as in the space program of the United States as a launching rocket. For example, were the first American astronauts with it brought into the orbit, or also probes sent to the moon or other planets with this Atlas rocket launching system. That is according to the Research Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ian Ridpath and John R. Shakeshaft on page 50. Also, what was it exactly? A rocket launch? Launching a rocket. Auriga. A prominent constellation of the northern hemisphere in winter. Auriga, which means the charioteer. I think we figured out in history that the chariot that was written was used either by Alexander the Great or the Egyptians. It was used by the Egyptians. It was part of the ancient weapons. A chariot is a vehicle. It's drawn by two horses, for example, and there are one or two people on the back, and one is steering the horses, and the other and steering the chariot, the vehicle, and the other one is doing war things, throwing spears and shooting arrows. I think that is a chariot. So a person on a chariot is a charioteer. Therefore, and Auriga, that is actually, I think I remember correctly, but Auriga was somewhere used in Latin, in the Latin language, when they were talking about the Romans, about I think the Circus Maximus. Somewhere I don't know where it came from. Auriga. Now, it's a prominent constellation of the northern hemisphere in the winter. So in the winter in the northern hemisphere, people might see Auriga, which means charioteer, and it lies on the edge of the Milky Way between Gemini and Taurus. Its brightest star is Capella. It is at the edge of the Milky Way between Gemini and Taurus. The brightest star is Capella. and it's called Auriga. I'm going to stop the camera and just try to say it. Auriga is a star constellation, and it can be seen in winter in the northern hemisphere. And it is between Gemini and Taurus at the end of the Milky Way, and the brightest star is Capella. And Auriga means charioteer, and a chariot is a vehicle drawn by horses. That is according to the Reader's Digest Library of Modern Knowledge, Book 1, Part 1, Structure of the Universe, written by Ayn Rand and John R. Shakespeare, on the page 50. Walter Baade, born 1893, a German-American astronomer who discovered, while studying the Andromeda Galaxy, that there were two populations of Cepheid variables, stars that are used as markers for measuring galactic distances. There are a lot of things with C. Cepheid variable. A star that constantly swells and contracts in size. And I think I think I know what it is. We have it in Celio signs. There's another thing. So there's the thing. The thing is, some stars are so massive that they are able, and so hot on the inside, that they're able to fuse the product out of a first fusion out of two hydrogen together to one helium. Again, the helium, it needs much more heat to press two heliums together to form a carbon and oxygen. That happens in these very big stars. And then that happens, they're having a much stronger outward force through that fusion together, through that fusion that has an outward force that it blows away the outward part. And when we're getting smaller again, and I think when it repeats again, they're changing the color. They're going from red to blue, or from blue to red, blue, and so on. They're blowing away the red part of the outside, and then the hotter blue part in the center is visible. And when it heats up again, and when it happens again, something like that. Now, let's look if we're talking about the same or something else which is similar. No, Cepheid variable, that is a star that constantly swells and contracts in size, varying in brightness as it does so. Cepheids have proved a valuable yardstick for measuring distances in the universe. Cepheid variables go through a cycle of light variations in periods ranging from 1 to 50 days. That is fast. Observations show that the real luminosity or true brightness of a Cepheid is linked with the period of its light variation. The true brightness of a Cepheid is linked with the period of its light variation. We're saying how bright it is depends on how long it takes until the next time it changes from bright to not bright. The longer the period, the brighter the Cepheid. This is known as the period luminosity law. So, when the period of a Cepheid is known, simply from observation, its real luminosity, absolute magnitude, can be worked out. Then, by comparing the star's absolute magnitude with its apparent magnitude, a measure of a star's brightness seen on Earth, its distance can be calculated. See also distance modulus. This method of measuring can be used for gauging, I don't know what gauging means, but it must be something, gauging distances in the universe that are too great for the parallax method to be accurate. Our 600 Cepheid variables are known in our galaxy, and they are also visible in other galaxies. They take their name from Delta Cepheid, the first of the kind discovered, with which varies in brightness every 5.37 days. The light variable of Delta Cepheid was discovered in 1784 by the English amateur astronomer John Goddard. Okay, there's a star and it gets brighter and not so bright from time to time. And how bright that star actually is depends on how long it takes until it gets the next time bright and not so bright. So if it takes just one day, then the star is not so bright. And I think I said if it takes a lot of time, 50 days, until it is the next time really bright and no, it just gets brighter, not brighter, then it is a very bright star. Whatever. Basically from that they know now how can calculate how bright that star is actually, that star there. Not just how bright it is seen on Earth. But because they now took it 1 day or 10 days or 50 days, they now from that calculation, the longer it takes, the brighter the star actually is. They can calculate and can say that star is exactly that bright. And when they look how bright does that star appear on Earth, because a bright light might be 100 meters far, barely visible. So they now know from the period it takes until it gets again bright, how bright that star really is, where it is, and they of course know how bright it appears on Earth. And by that they can measure how far that star is away, because they can put out how much light was lost, they know how much light was sent and how much has received, something like that. And when they're able to know, because how much light was missing, they know how much it was sent, they know how much comes there, they know how much is missing, they can calculate how far it's away. And therefore we have, everywhere that they have such a simple variable star in the universe, they know how far that place is away from the Earth. Walter Baade discovered while studying the Andromeda Galaxy that there were two populations of Cepheid variables, and these are stars that are used as markers for measuring galactic distances. Baade found that the original calculations based on a single Cepheid type were wrong. From his observations, he recalculated the distance of the Andromeda Galaxy from the Sun and found it to be 2.2 million light years away, more than twice as far as had been believed. Using this new Cepheid yardstick, it followed that all distances from other galaxies were greater too. Okay, in the past, in the 19th century, they knew just of one of these Cepheid stars, and I don't know what it exactly did, but they said it's the 10% of its brightness per light year, and they were wrong. It were the double amount, or the half. It was the half. Whatever the guess they took to say it is that and that was off by the half. But now they found two at the same place. Or something like that. Walter Baade found that there are two of these Cepheid things at the same place, and by comparing these two, it was been able to calculate exactly that and that. Because I don't have time to explain it probably, and I don't actually know how. But basically that is just two, and now it's able to compare them and found out how much it is. And now all the distances in the universe were recalculated, and basically all calculations now before 1930s or something were doubled. I think that is what I said. Now, we don't have time left, but it was more or less planned. We read another thing about Walter Baade in the next part of space science. We're going to continue here. So if you were here for space science, you can go directly to the next part of space science, where we're going to read Walter Baade again, and probably also think about of the Cepheid variables. We try to understand it a little bit better. If you stay here and participate in the body center training, it's on the screen. It's actually wrong. Legs standing hip width apart, down to the knees, flex the legs, press up together, straighten one leg. Bend it again. Our legs straight. Bend it again. A bit further apart, down, press together, and together, go out to one side. Out to the other side, press together, flex. Middle, and up. Now one leg. And press on the top against the knee. Riding with the leg, flexed foot, even and hips, taller with the back, and have a little bend. Press on the inside. Press up to the side. And lift your leg. And press down. Press on the side. And press up. On the outside, home slowly. Close again. Take our leg as well. And now on the ground, first on the elbow, this side leg. Now if you like one leg up. And on the long arm. arm out, leg up and pull the knee to your elbow. And over. Leg up. And on the long arm out, leg up and pull the knee to your elbow. And up again. One knee onto the ground. Pull the toes in. Move the leg from left to right. Outside. Pull the leg up. Step on. Take the leg to the ankle. Straight back. Step on. The next two sides. Breathing it out. In and close the legs. Breathing it out. It was the fastened body center training. I thank you very much. At next time.